Welcome to this NPTEL course on advanced pre-stress concrete design. Now we are talking about losses in pre-stress concrete, the module 2. Well, in the last lecture, we talked about the immediate losses that happens immediately after the pre-stressing. So we talked about the loss that is happening from elastic shortening of concrete and the loss that is happening from friction, that is due to curvature and wobble losses, and then we also talked about the loss that is happening from anchorage slip and how to estimate the force variation diagram. In this lecture, we are going to talk about time dependent losses. That's what we have here. And the time dependent losses, three important phenomena are there: creep of concrete, shrinkage of concrete, and relaxation of steel. All of them, they also induce losses in pre-stress. Okay. So the expected learning outcomes, the student will be able to understand how to estimate the losses in pre-stress due to relaxation of steel, and how to estimate the losses in pre-stressing due to creep and shrinkage, and also the student should be able to explain the theory behind the code provisions for the loss estimation using IS 1343/2012. Okay, so let's see what is relaxation of steel. And relaxation of steel is a phenomena. It's again like a creep happens in concrete. It is basically what we do in pre-stressing, we apply a constant stretching to the tendon or a strand. So the strain remains constant, but the stress required to produce this strain, constant strain, need not be same. In fact, the stress required to keep the strain constant will keep coming down over a period of time. This phenomena is called as relaxation. Okay, and this has to be taken into account. For example, for at any time t, under normal temperature conditions, the stress that is left in the strand after it is being tensioned to initially stressed FPI can be estimated by an equation, and this equation is this. Okay, and here you can see the time t is given in hours, and FPI is the initial pre-stress. Usually FPI is taken as 0.75 times FPK, where FPK is the characteristic strength of concrete. It could be 75% or 80%. Typically, we don't go more than 80% of the characteristic strength for applying the initial pre-stress. Different codes will have different limits. For example, if you look at IS 1343, the maximum limit that jacking stress can be applied is 76% of your characteristic strength, right? So you can see this equation can also be plotted, and in fact this is also experimentally measured by study by Magura et al. In 1964, one of the classical works. You can see in the y-axis, it gives an expression for the remaining stress Fp as a function of initial applied stress, and in the x-axis you have hours, time in hours, right? So if you look at this red color curve, which talks about stress FPI as a function of yield strength of the pre-stressing strand, if you apply initial stress very close to that of yielding strength, in this case it is 0.9, you can see here that the stress reduction is higher. So for example, at the initial stage you have applied let's say about 95%, and at the end of let's say 1 lakh hours, you are left with about 85% or so. So you can see here that about 10% reduction is there happening in the stress. Initially it was 95, but at the end of 1 lakh hours, 100,000 hours, it has become 85% of your initial stress. So that means there is a reduction in stress, and there will be a reduction in your pre-stressing force. The beneficial effect of pre-stressing will then come down, which we need to account in our design calculations. So in this equation, if you are using low relaxation steel, then instead of 10, we have to use 45. Okay. Typically nowadays in the modern construction, we use only low relaxation steel. So in this equation, instead of 10, we have to use 45. In the olden days, people are using stress relieved strand, and that the value is 10. But if you are using low relaxation steel, we need to use 45. Now, there is also a reduction coefficient. You can see that the creep and shrinkage of concrete, because of that, the strain in the pre-stressing steel will reduce with time. And this, in fact, will have a beneficial effect of reducing the relaxation loss. So, that means because of the effect of creep and shrinkage, the relaxation loss will come down, which somehow we have to account for that. So, that is usually accounted by this reduction coefficient xi r. And now, let us see how this xi r is varying with respect to thing. So, in the y axis I am plotting this reduction coefficient, right, and in the x axis I have the total pre-stress loss minus the intrinsic relaxation loss divided by FPI, and we know FPI is always the initial pre-stress, and typically we take it at 75% of your characteristic strength. So, if you look at this curve for a particular value of x value, let us say at this 0.3, and you see here that the reduction coefficient is going to be, let us say in this case is about 0.32 or so like that, right, when this value is high. But if the ratio of initial stress to ultimate strength is higher, right, then you see here the reduction coefficient is working out to be 0.55 or so. So, what does it signify is, if the initial stress is less, again the reduction coefficient is low value, that means the loss is also going to be less. So, that is what the implication. So, somehow we have to account for that. Okay. Now, why that relaxation is important? What does it actually does? So, in a way, the relaxation, we know that strain remains constant, but the stress is coming down. So, that means the elastic modulus, the definition for elastic modulus is stress by strain. So, for a particular strain, if the stress is coming down, in a way we can say that the stiffness of the steel is somewhat getting reduced. So, that is what we are saying. So, the effective steel stiffness basically can be calculated by accounting for this reduction coefficient as well. Okay. Now, you know FPI, depending upon the time that you are calculating, FP can be calculated from the equation that we discussed previously, and EP is elastic modulus of steel, and typically it is 2 into 10 to the power 5 megapascal, or slightly lesser for pre-stressing steel. Usually it is about 1.95 or so, and you can calculate your effective modulus like this. And this is what we said. You have stress in the y-axis, strain in the x-axis. Let us say I have initially stressed to a particular strain at this location. Let us say this is your epsilon pi. When this, if I am keeping it constant, but the stress need not be constant, it will keep coming down over a period of time. So, you see here at this point, initially this was this FP, let us say FP1, and this has come to FP2. So, it has come down. So, in a way what we are saying is, that means if you take the effective slope, the stress, the elastic modulus can be calculated by Fp2 by epsilon pi, and you see that there is a reduction in your material stiffness. So, this equation basically helps us to capture that reduction in your material stiffness. Now, let us look at how the IS 1343 handles this relaxation loss, and you can see here that it gives a very simple values in terms of percentage of loss, and it categorizes as for normal steel and low relaxation steel, and these are all from experimental values, experimental measurements that was done, and they are reporting at 1000 hours. When I am stretching it and I am keep measuring the stress over a period of 1000 hours, at the end of 1000 hours, at this particular temperature, what would be the loss? And what you observe here is, if the initial stress, this is FPI in the equation, if this initial stress is higher, let us say at 0.8 FP, here FP means characteristic strength, and sometimes we denote that as FPK as well. You see here, if the initial stress is close to that of characteristic strength, your loss, relaxation loss also for both categories of steel, it is higher. So that means one way for us to reduce the relaxation loss is to not get very close to that of yield strength or characteristic strength. So initial stress, that is the reason there is a maximum limit that is enforced by the code on the initial stress that what you can apply to the pre-stressing steel. So, but these are all, please note that these are all the values for 1000 hours at this temperature. Now, if I want to calculate the loss for, let's say, 10,000 hours or 20,000 hours, either you can use the equation that we discussed in the previous slide, or the code is saying that you can multiply this by 3 to have a conservative estimate. To me, this may be slightly on the higher side, but you can use the equation that was discussed in the previous slides for exact calculation of the relaxation loss, depending upon the time at which that you are calculating. Right. Now that we have studied relaxation, let's see what are the losses that happens because of the creep of concrete. And again, what is creep? What are the factors affecting creep? And how to estimate the creep coefficient? All of these things were discussed in module 1.3 in detail. You can refer to that first week contents. In this section, we are going to just discuss how to estimate the creep losses and how the IS code provisions are accounting for the loss due to creep. Okay, and due to creep strain in concrete, there will be a loss in the pre-stressing tendon, and that is what we are calling that as a creep loss. Right. So now let's see. This is the variation of your strain that you have discussed in the first module, and this is your initial strain that you are applying due to load. Though the load remains constant at this point, or let's say epsilon instantaneous strain due to this is due to load, right? But the load remains constant, but the strain in the concrete doesn't remain constant. The strain keeps on increasing. Initially, the increase in strain is higher, but at a later point of time, it plateaus and then it goes all the way here. So if you see here, the total strain is this. Right, that we discussed it in the previous. This is the epsilon total, which includes instantaneous strain that is happening from load and then the additional strain that is happening from creep. Let's say if I am removing the load, you will recover some part of strain, some part of creep strain also will be recovered. However, there will be always permanent strain that will be locked in, that we have discussed it in the previous module. Now, depending upon what time that you are calculating the losses, we need to see what is the value of creep strain, right? So that is the important thing. Okay. Now, the ultimate creep strain is proportional to the elastic strain that we have studied it. And usually, when the stresses are less than 1/3 of the characteristic strength of concrete, that means let's say 40 megapascal concrete, 1/3 of, if I applied stress is less than 1/3 of 40, then we say that creep strain is actually proportional to the elastic strain that you apply because of the loading. Now, the loss in pre-stress delta Fp due to creep can be calculated from elastic modulus of pre-stressing steel multiplied by the creep strain or ultimate strain. Now, we also talked about creep coefficient, which is theta, or sometimes we also call that as phi, which is your creep coefficient, right? Now, this creep coefficient is basically phi is nothing but epsilon creep ultimate divided by epsilon elastic. So, that means the total strain due to creep divided by elastic strain is nothing but your creep coefficient. So, now if epsilon creep ultimate is epsilon elastic times phi, so that is what we are written here, theta into epsilon elastic. Theta and phi, they are all same. These are called creep coefficient. So, we can say that theta into epsilon elastic is epsilon creep ultimate strain, and if I am expressing in terms of elastic strain, we know that now that the strain is what I am applying is less than 1/3 of the characteristic strength, the material is going to be in the elastic regime. So, I can define the strain as stress by elastic modulus like this. So in a way, now EP by EC, you know, it is a modular ratio. So I can calculate this delta FP due to creep as modular ratio times the creep coefficient times the stress in the concrete, right? So always we try to measure the stress in the concrete and then express the losses in terms of that, right? So the ratio of, as we have defined, the ratio of ultimate creep strain to elastic strain is defined as the ultimate creep coefficient, or simply creep coefficient theta, or sometimes we also write that as phi. Okay. Right, now let's see how the IS code provisions are taking care of the creep of concrete. These are all explained in the section 6.25 of IS 1343 2012. And this gives a very nice table, and you can see here there are several factors that are listed here, and this gives you the creep coefficient at 70 years. So you can see that this is the maximum coefficient, creep coefficient that can happen. You saw that the creep variation also somewhat it becomes plateau. So it becomes flat and there is no absolutely change after 70 years. So this is the maximum value that is possible for a given concrete. Now here you can see it also function of the age of loading. Again we said when the curing has not happened properly, when you start loading the member at an early age, then the creep will be higher, right? That is the reason if you look at one age of loading, 1 versus 365, you see for any of these coefficients. Now again there are two columns that are given here. One is for a dry condition where the relative humidity is 50%, and another one is a humid atmospheric condition where the relative humidity is 80%. Again we have discussed what is the role of relative humidity in the first part of the first module. So you can go back and look at it. In general, a drier climate will induce more creep because it is going to absorb the unutilized water that is in the concrete system. In that process, the creep will be more. So that is the reason if you see the values for dry conditions for creep coefficients are higher than the humid atmospheric condition, right? So same. There is one more factor called notional size coefficients, which we typically call that as H0, which is given by 2 into AC by U. Now what is, it is in a way, it is a ratio of volume by surface area, okay. So if I take a unit length, right, volume will be the cross section area multiplied by that length. Similarly, perimeter multiplied by the length will give me the surface area. So that's how we denote this notation. Notional size coefficient is H0, which is a function of volume of concrete divided by the surface area that is exposed to the outside environment. Now you can see here, now that the volume is at the top, when the H0 is getting more and more, your creep coefficient will come down, right? So for a particular volume, if my surface area is more, then the creep will be higher, right? So when will the surface area will be more? When the H0 is less. So that's why for H0 of 50, creep coefficient in this case is at age of loading of 1 day is 5.8. However, when H0 becomes 600, this becomes lesser value of 3.9. So in this way, the code is giving you a very simplified method of calculating the creep coefficient depending upon the H0 factor and the age of loading. Now let's look at shrinkage losses. What is shrinkage? And again we have discussed about shrinkage in the previous module in the part 3 of the module 1. In this section we are going to discuss how to estimate the shrinkage losses and IS code provisions. Now the loss in pre-stress in the pre-stressing tendon due to shrinkage strain in concrete is defined as the shrinkage loss. When concrete is shrinking, the stretching in the pre-stressing tendon is also going to come down, right? So that is the reason that we need to account for this loss that is happening from shrinkage. Now in shrinkage strain, typically we have shrinkage that is happening from drying shrinkage, epsilon CD, and then we have shrinkage that is happening from autogenous shrinkage. We also have one more thing called carbonation shrinkage, but typically the carbonation shrinkage is not very high. unless you are talking about a CO2 rich environment where the member is there, then there also CO2 shrinkage may be higher, carbonation shrinkage may be higher, but typically it is not a controlling factor. So, that is why we include only these important shrinkage strain, which is a drying shrinkage strain and autogenous shrinkage strain in the loss calculations. Now, what is drying shrinkage? Again, we have discussed this in the previous model. It is a water loss due to the environment, and autogenous shrinkage that happens from water loss that is happening because of the hydration process that happens in concrete. Now, this in a simplified way, the total shrinkage strain is as added as a addition of your shrinkage strain from drying shrinkage and autogenous shrinkage strain. So, epsilon CD plus epsilon CA gives me the total shrinkage strain. Now, how do we estimate that? The code is again saying that epsilon SH is nothing but epsilon CD plus epsilon CA. That is the total amount that stretching in the pre-stressing steel is getting lost. So, that strain multiplied by the elastic modulus of pre-stressing steel gives me how much the shrinkage strain is getting, so how much losses that is happening because of the shrinkage in concrete. Now, all the equations that are there are explained in section 6.24, and typically for autogenous shrinkage, what we are assuming is higher the grade of concrete, higher will be the autogenous shrinkage. So, here tactfully what we are assuming is when you need high strength concrete, you will put more cement. So, more will be the loss of water due to the hydration process. So, this is an assumption, but of course, the same grade of concrete can be done by multiple ways, but in general what we are assuming is higher the grade of concrete, higher will be your binder content and higher will be your water loss that is happening from hydration process. That is the reason for M60 they are assuming 95 into 10 to the power of minus 6 strain compared to M30 which is having only 35, roughly about 1/3 of what you have for M60. Right. Now, these are the maximum values that the code is giving. Now, depending upon the time, let us say I am doing it at 1000, let us say 1000 days or 300 days, the shrinkage actually happened may be different, right. So, that is the reason the code is saying this is the maximum value, and this is being reduced by a reduction factor which is beta AS, which is expressed as a function of time t. Now, what is beta AS is again it is an empirical experimentally calibrated equation, and you can see here as with respect to function of time t in days the reduction factor. So, if t is very large, then beta AS will approach unity, which will become close to 1. If t is very small, then beta AS factor will be low, then only a fraction of that what is the maximum value you have to consider in your design. So, that is what the code is giving. Okay. Now, we have talked about autogenous shrinkage. Similarly, for drying shrinkage also the code is giving you, and this is the maximum value, drying shrinkage value. This has to be reduced by two factors. One is the KH factor, humidity factor. Another one is your another reduction factor which is given as a function of your time t, and this beta ds factor, reduction factor, again you can see here where t is the time at which that you are doing the calculation, ts is the time up to which you have cured the concrete. So, when you cure the concrete, let us say you put the cube in water, there is no way of water escaping the system because of the drying, right. So, that is the reason. So, the amount of time that you are curing also should be considered this as a part of the equation. In addition to that, the H0 factor that we said, volume to surface area factor also is built into this equation. You can see that you have the square root and all. And these, when you see this kind of form, you can clearly see that it is an experimentally calibrated reduction coefficient. Now, what are the maximum value that the code is saying? Again, you have two types of things. One is for a dry climate, one is for a humid climate, and you can see higher the grade of concrete. Now, here you can see here it is the lesser. Now, why do we say that the drying shrinkage is taken as lower value compared to that of 25 megapascal? So, here again tactfully what we are assuming is when you are using high strength concrete, the water cement ratio that you're going to use is going to be lower. So when you have a lower water cement ratio, then the free water that is available for escaping will be less. So because of that only, drying shrinkage values for high strength concrete in the code is taken to be lower value compared to that of low strength concrete. And as expected, when you have a humid environment, already there is a moisture in the air, so it is not going to absorb the escaped water easily, right? So when you have a humid system, then the drying shrinkage values are expected to be lower compared to that of drier climate, where you will have higher drying shrinkage values. So that's how this code is giving you these values. Now we also have a reduction factor based on the KH, right? Depending upon your notional size coefficients, you have KH factor is defined, and again higher the H naught value, lesser will be your KH factor. So you tend to use lesser value of your strain as a drying shrinkage strain in your calculations. Again H naught we have already defined, which is the notional size coefficient, which is defined as 2 into area of the cross section divided by the perimeter of the cross section. Now again, what is TS? TS is the age of the concrete at the beginning of drying. Okay, so normally this is at the end of the curing. Again, depending upon what kind of curing that you do, whether you're doing steam curing or you're doing the normal water curing, you have to account for that equivalent days of curing, so that the code gives you how to do that.